As you may know, I'm a theoretical physicist. Explaining my job to non-scientist friends or even family members can sometimes be challenging. Hey, happy Thanksgiving. Sorry, I'm a little jet-lagged. I just got back from China.
China, we love China, folks. Did you meet Xi Jinping?
No, I wish. I was just at a conference, so we were mostly having lectures.
You had elections? We shouldn't have elections, folks. Mail in ballots are very nasty.
No, Grandpa, lectures, not elections. I was in China for a physics conference to talk about my work. Okay, it's not actually that bad, but conversations like this have made me realize that many people are curious to learn more about what the day-to-day workflow of a theoretical researcher looks like and why travel is such an important part of that process. I just got back from a visit to Caltech, who very nicely invited me to come and give a seminar about a paper that I recently wrote with Jim Halverson, who's a professor at Northeastern, and Aaron Mutchler, who's a very talented PhD student. Now, I won't subject you to some sort of get ready with me type video or like a travel vlog or anything like that, but maybe I'll tell you a little bit about what my visit looked like. So I left Boston on Tuesday and flew from Boston to LAX, took an Uber from there to the hotel, and then despite being completely exhausted, I had to finish my slides for the presentation. The next day, I got up early, headed over to Caltech's campus, which is very pretty, and met up with an old colleague to catch up over coffee. Then my talk was at 11 a.m., and I think it went pretty well. There were a lot of good questions and remarks from the audience, and I think those comments actually helped improve my understanding of my own work. After that, the group took me out to lunch, and we chatted more about physics while eating outside and enjoying the lovely Pasadena weather. Then I had more discussions with people in the afternoon, and the group took me out to dinner, so we chatted more about physics while having some awesome sushi. The next day, I again got up early to have discussions with a different group that focuses more on AI for mathematics, got a very nice tour of Caltech's campus, and chatted with those guys until around noon. Now, at that point, I had to very quickly say goodbye to everyone and call an Uber so that I could go right back to LAX and catch my flight to Boston. So, if you've never traveled for academic reasons, like a seminar or a conference, one takeaway is that these visits are packed and extremely stimulating. I was basically always chatting with people, brainstorming ideas at the blackboard, discussing both my work and their work, and trying to learn together as much as possible. We have some idealized view of the scientific method in our heads, but at a practical level, the method that I follow in my work goes more like this. Step 1. Think very hard about problems that no one has solved. Step 2. Have discussions with people who are much smarter than me. Step 3. Repeat until either the problem is solved or we give up. Step 4. If solved, write a paper about the solution. Step 5. Travel to give a talk about the paper and chat with people to come up with more hard problems. Anyway, so what was the problem we actually solved? I've been interested in connections between neural networks and quantum field theory. Now, I won't be able to do full justice to either of these subjects in just one video, but along the way, I'm going to recommend some other great YouTube videos that you can watch if you want to learn more, and I'll put links in the description. You've probably heard a lot about neural networks. They're artificial intelligence tools, but at a basic level, they're just functions of the same type that we learn about in math class. In the simplest example, they just take one number as input and give you some other number as output. More generally, you can think of a neural network as a sort of black box that can take in many numbers as input and give you many numbers as outputs. Now, the specific outputs that a neural network gives you for a particular set of inputs are controlled by parameters, which are some other set of numbers that define the neural network. In the sorts of neural networks that you may have seen pictures of, these parameters are called weights and biases, which are labeled by W's and B's in this picture, respectively. By the way, I highly recommend this set of videos by 3Blue1Brown if you want to learn more about neural networks, and I'll link to it below. On the other hand, what we call quantum field theory is really a framework for building different theories in physics. One example is the standard model of particle physics, which you may have heard of, and which we test in experiments like the Large Hadron Collider. The standard model has different fields to represent different particles, like the photons which make up light, or the electrons that appear in atoms that we learn about in chemistry. So what is a field? In the simplest case, a field is another gadget like a function that takes in some numbers and spits out some other numbers, but with a different interpretation. Imagine a temperature grid on a plate of metal. I could give you three numbers, where the first two numbers are the x and y coordinates of a point on that grid, and the third number is a moment of time, like 1 second, and you could go and measure the temperature at that point at that time and get a number. So three numbers go in, and one number, maybe 233 degrees Fahrenheit, comes out. But the fields in quantum field theory are a little different from that in two main ways. The first way is a somewhat technical math fact, which is that quantum fields are a little too rough or spiky to be honest functions. If I try to measure the value of a quantum field at a point, I actually get infinity. But what I can do is smooth out the field by computing its average value over some region, and that does give me a number. Spiky objects like this are technically called Schwartz distributions, but for the purpose of this video, you can ignore everything I just said and pretend that quantum fields are regular functions. The second difference is that quantum fields fluctuate randomly. What that means is that you shouldn't think of the value of a quantum field at one point in space and one moment of time as something that returns a single fixed number. You should think of it more like a roll of the die, which could return any whole number between 1 and 6. So, neural networks are functions, and quantum fields are some kind of random functions. The idea that Jim and friends came up with is to ask, can we think of quantum field theories as sort of random neural networks? Now, remember I told you that neural networks have parameters like weights and biases? So when I say random neural network, all I mean is that we choose those parameters randomly. Each roll of the die, each choice of parameters, then gives us a different random neural network. This idea is called the neural network field theory correspondence, and if you want to learn more about it, I helped the ScienceClic channel make a YouTube video partly about this subject, which I'll link to in the description. Okay, with all of that said, what did we actually do in the paper that I spoke about? Well, there are two main pieces. First, we showed that if you make certain assumptions about a quantum field theory that you want to study, then it can always be represented as a random neural network. So, at least in those cases, the answer to Jim's question is yes. In the second part of the paper, we actually did this for an example. Now, in string theory, there's a certain quantum field theory that we like, which is called Liouville theory. Or in France, we say Liouville theory. Oh, it is a flaky croissant. Let me back up just a little bit. If you imagine like a particle moving around in time, it traces out a curve, which we call its world line. And similarly, if you have a string moving around in time, it traces out a little curtain, which we call its world sheet. In 1981, Polyakov was working on defining world sheet string theory using something called the Polyakov path integral. And in doing that, he discovered that Liouville theory plays a particular role. So with Jim and Aaron, we asked, can we build Liouville theory using a neural network? And the answer is yes. We built it, we ran it on a laptop, and we were able to perform numerical simulations. I'll just show you one plot, and all you need to know is that the solid colored curves represent the true answers for something that you can compute in Liouville theory, while the colored dots represent the numbers that we got when we ran our neural network simulation. And the dots agree with the curves to within 1% accuracy. So it seems like our neural network is doing the right thing. Just to clarify one possible confusion, since I said before that neural networks take in numbers and spit out other numbers, we did not just train a neural network to spit out the raw numbers that are appearing as the colored dots in this figure. Instead, we cooked up a neural network that represents the Liouville field itself. And then we rolled the dice 500,000 times, generated 500,000 examples of the Liouville field, and used those examples to compute a derived quantity, which is then compared to the right answer. So all you need to know is that in our setup, the neural network is the quantum field itself. And I think that's very cool. You might even say that it's a new way of doing quantum field theory on a computer. So that was my trip to Caltech, and that is what I spoke about. Did anything surprise you about the way that academic travel works, at least in my field? And do you find this neural network field theory correspondence as cool as I do? Let me know in the comments, and thank you for watching.